Hi, welcome back. This is the second video of Chapter 8 for Physics 125 at Lewis and Clark. So we really covered in the first chapter, in the first video, most of the critical concepts about kinetic energy, which is energy of motion, potential energy, energy of position, primarily gravitational potential energy, the potential you have to move because you're going to fall. And we talked about work, which is a force times a distance, a force applied through a distance when the force and the distance are parallel. And we talked about power, which is the rate at which work is done or energy is consumed or energy is given. It's just work and energy, which are equivalent to one another through the work-energy theorem divided by time. That's power. So now we're going to work on a number of different examples. We did a few examples last chapter. We ended up here with a number of conceptual examples about different ways to go from potential to kinetic and potential to work and work to potential and so on and so forth. And we ended here with the idea of a roller coaster, that the roller coaster does work on you to pull you up to the top, and then you slide around, and then your potential energy, which is a lot at point P, starts to decrease as you fall. Your height decreases and you gain velocity because of that, right? Just the same as we did with kinematics, that gravity accelerates things downward, but now we're thinking about it in terms of energy. You lose height, you lose potential energy, you gain velocity, you gain kinetic energy until at the bottom of the hill you're going very fast, which is very exciting. And then you proceed to go up and around all the other hills, which are subsequently shorter than the first hill because you do lose some energy due to friction. So what we're going to do now is a computational example of a roller coaster. A computational example of a roller coaster with no friction, just because that makes our life simpler mathematically. We will do other problems with friction a little bit later, but for now we're going to pretend that our roller coaster has no friction. So we see here our roller coaster cart is right about to fall down the first hill, so it has a velocity of approximately 0. Obviously, if it's not moving, it's not going to fall, but we're going to call it 0 to keep our kinetic energy 0 at the top of the hill. And its height to begin with is 60 meters. And we are going to examine how fast the roller coaster will be going at point A, at point B, at point C, and finally at point D. And we are given all of those points' heights, right? So B is at 20, C is at 30, D is at 40, and A is at 0, and we start out at 60. That's very important. If we are given all the heights, then we can find the potential energy. If we can find the potential energy, then we are able to find, by subtraction, the kinetic energy, and correspondingly from the kinetic energy, the velocity. So let's go ahead and work on this problem. We just made the problem a little bit smaller up here so we have room to work. Again, a reminder, potential energy is mgh, the mass of the object, times the acceleration of gravity, times the height it is above whatever consistent point we decide to measure that height from. Usually it's the height of the ground. And the kinetic energy, Ke is kinetic energy, it's 1/2 the mass of the object times the velocity of the object squared. So what I want to point out here is that every point on this roller coaster is in essence the same. It's the same in that if you take its kinetic energy at that point and you add the potential, you'll get the total energy. And if you pick a new point, at A, the kinetic plus the potential is the total. At B, the kinetic plus the potential is the total. At C, the kinetic plus the potential is the total. And at the beginning point, the potential plus the kinetic is the total. So again, this is this idea of conservation, which we covered last time, that energy cannot be created or destroyed. It's going to be there somewhere in some form, and that's what allows these equal signs to be very powerful. So the problem says we're supposed to be finding the velocity at B, C, and D, but we're going to find the velocity at A first, right? That's the most exciting velocity. That's when we're going to be going the fastest. So the first thing we need to do is look at the top, right? The top is the only point in this entire exercise where we've been told the velocity and the height. So we know everything about the top, and that way we'll be able to find the kinetic energy of the top, add the potential energy of the top, and that will give us the total energy. And that will be the total not only for the top, but for every step in the problem. Every step has the same total energy. So at the top we have a velocity of 0, a height of 60. We just got those off of the diagram, the problem. And so then we go to do the calculation, right? If the velocity is 0, well then 0 times anything is 0. So we get our physicist's favorite number, 0. So the kinetic energy piece is 0. The potential energy, though, is mgh. The mass of the cart was 1,000 kilograms. Gravity is 9.8, and the height is 60 meters. So you multiply all those together, and if you take kilograms times meters per second squared times meters, you'll get a kilogram meter squared over second squared, which is a joule, which is why I gave this answer in joules. Now this 588,000 joules is very important. This is the total, and it's going to stay the same for the whole problem. The whole problem is going to have this total, okay? Okay, because energy is conserved. So at every single point, we know that our sum of kinetic and potential should add up to this number, okay? So that was the preliminary part. Now we are interested in point A, So again, it's kinetic at A plus potential at A has to equal 588,000, okay? At A, the height is 0. Again, we get physicists' favorite number kicking in. If the height is 0, then 0 times anything is 0. So the potential energy term here is going to drop out. It's just going to be a 0. So now we have 588,000 joules equals just our kinetic energy, which is 1/2 mv squared. Okay, that's good because we're supposed to be finding the velocity. So that's our unknown. We do know our mass, it's 1,000. So we plug in the mass. 1/2 of 1,000 v squared has to equal 588,000. So half of 1,000 is 500. So now we have our total equals 500 v squared. We divide both sides by 500. The 500 here on the right side will drop out, and on the left side we'll get 588,000 divided by 500, which is 1,176. So we get that 1,176 equals v squared, and then we take the square root of both sides, yielding us a velocity of 33.4 meters per second. So now we've gone from the top of the hill to the bottom of the hill. We've been able to calculate the velocity of the cart at the bottom of the hill. So now we want to move on and do the other steps. They're slightly more complex because we don't have the nice convenient 0 that makes one of our terms disappear, but they're not that much different. So if you want to rewatch to see how I did all of this, you're welcome to do that, but then we're going to flip on to the next slide and do what's going on at point B. So again, this 588,000 joules, this total stays the same for the whole problem. We're still in this problem, so we can still use that total. We don't have to recompute what's going on at the top because those numbers haven't changed. So now for point B, kinetic plus potential has to equal this total, okay? So now we have a height of 20 meters. So we're going to be up in the air here a little bit at point B. We're at the top of the loop. We're upside down, but that really, energy doesn't care whether you're upside down or not. That's not part of its computation. So we're at a height of 20 meters. We still have the kinetic energy term. Now we have to add the potential energy term too. These two terms together have to equal our 588,000. So we have 1/2. We still know the mass is 1,000. V we do not know. We do know the mass potential energy equation here. The mass is 1,000, gravity is 9.8, and our height is 20. So we've got this part that's got a variable, and we got this part which will all be a number, okay? So we move on to the next step. We subtracted that number across, right? So if you multiply this out, it's 196,000 joules, okay? So we've got the kinetic energy plus 196,000 joules. So we're going to subtract the 196 from the total. That was what was in our potential. The total minus what's in our potential. When we do that difference, we will get what's left, and what's left is in our kinetic energy. And our kinetic was 1/2 of 1,000, so 500 v squared. So you subtract those, you get 392,000. You subtract the 392 by the 500. The 500 drops on the v squared side, and we get 392,000 divided by 500 for 784 equals v squared. And then we take the square root, and we get 28 meters per second for our velocity at B. So at A, we were going 34 meters per second. Now we've gone up to B. We're higher. As we go up, we lose kinetic energy and we gain potential. So we've gone from 34 down to 28. We're going slower. And again, if you've ever ridden a roller coaster, you know that. As you go back up the hill or as you go back up the loop, the roller coaster slows down as you gain the height, okay? So we have that experience. So now we found for A and we found for B. So now we're going to move on and figure out what it is for C. And we're going to see here for C things are very similar, okay? Even the whole line of text looks very similar, but we are now doing the kinetic energy at C, the potential energy at C, and now the height is 30 instead of 20. So we still have a kinetic term plus a potential term, right? That's always the sum of the kinetic, the potential, and potentially any work that was done, but we don't have work being done by friction because we're pretending there's no friction on this roller coaster for now. So the kinetic term plus the potential term, we know the mass that was given to us in the problem, we plug that in. We know gravity is 9.8 and we're told the height is 30, okay? So again, we have a kinetic term with a v squared that we don't know, and we have a potential term that is fully determined. So again, we do the total, which still has not changed. The total minus what we got. What we got actually was exactly half of the total. It shouldn't surprise us. We're exactly halfway back to the top, right? We have a height of 30 instead of 60. So that gives us 294, which is half of 588. When you subtract them, you still get 294, right? We subtract half, we have half left. We divide that 294 by the 500, and we get 588 equals v squared. Now v is 24. So we had 34, 28, 24, and we could go on and do the same thing with part D. Part D has a, read the height because my face is in the way. There we go. So part D has a height of 40. So we would do this very same thing with a height of 40. We would be subtracting the 392. We'd get 196 divided by 500, and we would get a progressively smaller velocity because we're even higher. We're not going to take the time to work through that whole part. Hopefully you can see by now the pattern that we've established, and this is really the pattern that we're going to use over and over in these conversions between potential and kinetic. So now that we've done that roller coaster problem, we're going to go on to some other examples. Okay, what is the potential energy of a 65 kilogram Mr. Rassi at the top of a 4-meter ladder? So this is a little bit simpler problem to begin with. What is the potential energy? We're simply being asked for the potential energy. So we recall or we look up that potential energy is expressed as the mass times gravity times the height. So we were given a mass, we're given a height, and gravity on the Earth is known. So we have all the variables that we need. We plug those in. 65 times 9.8 times 4 equals 2,550 joules at the top of the ladder. Now, that might seem a very simple problem. We're going to go on to do part 2 where we will get a little more complicated. How much work did he do climbing the ladder? How much work did he do climbing the ladder? And here's where the problem maybe could be a little more complicated, right? We have two possible equations for work. We have our original equation for work, force times distance, and then we also have the idea that work is equal to the change in energy. So what we're going to see is that in this particular problem, we could solve it either way. One way is clearly easier, but we could solve it either way. Sometimes you can't solve it both ways, and so you've got to make the decision and make the evaluation of what information was I given. Those are the numbers I'm given, so that's the way I should solve the problem. So first of all, work equals the change in energy, right? And kinetic energy really isn't playing into the equation. At the base of the ladder, he wasn't moving. At the top of the ladder, he's not moving, so the kinetic is 0 in both cases. We're not even going to talk about the kinetic. What changes between the base and the top of the ladder is his potential energy. So if we take work equals change in energy, that's going to be the potential at the top minus the potential at the bottom. That's how much his energy changed as he climbed the ladder. Remember, it's always final minus initial. He ended up on top of the ladder, so it should be top is final minus bottom is initial. So potential energy at the top minus potential energy at the bottom, well, that's pretty easy. We have the potential energy at the top. We just calculated that in the previous step. And the potential energy at the bottom, well, he'd have a height of 0. And 0 times anything is 0. So we get our 2,550 joules minus 0. We get 2,550 joules as the amount of work he did climbing the ladder. But does that check out? Does that check out with our other way of doing work? Our other way of doing work is force times distance. So what force did he have to apply to climb the ladder? And what distance did he go going up the ladder? So work equals force times distance. The force he has to apply is equal to his own weight, right? He's got to lift himself up the ladder. That is why climbing ladders is difficult, is work, literal physics work. We have to lift our own weight up that ladder. So He's got a force equal to his own weight, or maybe slightly in excess of his own weight so that he actually moves. A force equal to his weight, and then the distance he moves is the height of the ladder. And these will produce a work, right? The force arrow is downward and the distance arrow is upward, and so those are parallel, and so we do have work being done here. So what is his gravity force? What is the weight of him? Well, that's his mass times gravity, right? Gravity force equals mg, or weight. And I don't want to represent weight with a W here because our W is already standing for work, and that could confuse the problem quite a bit. But our force of gravity is mg. So we take m times g, and then the height is the height of the ladder, or the distance is the height, and the height is the height of the ladder is 4. So 65 times 9.8 times 4, which should look vaguely familiar to you because we did exactly 65 times 9.8 times 4 up here. And we got the same answer, which we would expect, right? Because again, work is equal to the change in energy. So we got the work both ways. We got work by doing change in energy. We got work by doing force times distance. They came out to be the same number, the correct number. So what was his potential energy on top of the ladder? We did that. How much work did he do climbing the ladder? Now we're going to do the how fast would he be going when he hit the ground if he steps off the ladder. So if you step off the ladder and you just fall, and I just like to point out, I have no interest in stepping off of a 4-meter tall ladder. That would be approximately a 12-foot tall ladder. I do not want to have that experience. But if that had happened, how fast would he be moving when he hits the ground if he steps off? So we know how much potential he has at the top. We know how much potential he's going to have at the bottom, right? We talked about that already with the work. So potential, he's got some at the top, he's got none at the bottom. Kinetic, if he steps off the ladder, he's not going to be moving yet. So he's got no kinetic at the top, and he's got a bunch of kinetic at the bottom. So like I mentioned previously, you're going to get a lot of these problems where it's kinetic plus potential at the bottom equals kinetic plus potential at the top. But at the top, the kinetic is 0, and at the bottom, the potential is 0. So it simplifies down to simply being the kinetic energy at the bottom equals the potential energy at the top. And just to reiterate that, the potential energy depends on the height. If you're at the bottom, then your height is going to be 0. So 0 times anything is 0. That's why the potential term goes away here. And your kinetic term depends on your velocity. And at the top, if you're just about to start falling but aren't falling yet, then you would have no velocity. And so 0 squared times anything is still 0. So that's why the kinetic energy term goes away. So sometimes I jump really quickly to, oh, kinetic at the bottom equals potential at the top. And people are like, well, why? How do you know that? Well, that is the physics. The physics of this problem is realizing that at the top, your velocity is going to be 0, and at the bottom, your height is going to be 0. Once you get to this point, the problem becomes algebra, right? We have the algebra equation for kinetic energy, algebra equation for potential energy, and we have the numbers, and we put them in. So a height of 4, a gravity of 9.8, a mass of 65, 1/2 a mass of 65, and a velocity squared that we don't know. So when we plug all the numbers in, we end up with only one variable. Notice the 65 shows up on both sides, and we're going to talk more about that later. But when we divide by 65, the 65 on both sides cancels out. And then to get rid of the 1/2, we multiply by a 2. 2 times 1/2 would be 1. And so we need to multiply by 2 over there. And we get 2 times 9.8 times 4. This was our right side after the 65's dropped out, and we brought the 1/2 over. So we got v squared equals 2 times 9.8 times 4. So those three numbers multiply together to get 78. So then the square root of 78 equals the square root of v squared. So v equals 8.8 meters per second, which doesn't sound very fast, but you really don't want to hit the ground going that fast. I don't want to hit the ground going that fast. So here we had a problem kind of broken down into a couple of steps, talking about potential, talking about the relationship between work and energy, and talking then about how potential gets converted into kinetic as you fall off the ladder. So here's an example that does involve friction. So my oldest nephew's named Carl. If he was to climb up a ladder onto a slide, which again, this is a pretty tall slide, about 15 feet tall almost, 15 feet tall slide, 4.8 meters tall slide, climbs up the ladder, and then as he slides down the slide, he reaches a speed at the bottom of 4.5 meters per second. So how much work is done by friction on him? So this is a little bit different problem than we've been given in the past. We're given the height at the top, so we can find the potential energy. That's not unusual. But we also know, again, that his velocity at the top would be approximately 0. We know that his height at the bottom is going to be 0 because he's come down to the bottom, but they gave us the velocity, right? The roller coaster problem and that last problem with the ladder, our job was to find the speed at the bottom, and now they're giving us the speed at the bottom. And that's what's going to happen if they're going to ask us about friction, because now we have another term involved. And so if we're going to have a new unknown, we got to have our old unknowns be known. So what do? We say that at the top, he has potential energy, but he doesn't have any kinetic. At the bottom, he's got kinetic energy, but then we also have to add in the work done by friction. Now, does that mean the work done by friction is at the bottom? No, that's not what it means. But what it tells us is that however much energy we had at the top, some of it's going to be present as kinetic energy at the bottom, and the rest of it had to be consumed by work on the way down, right? The friction between his rear end and the slide is where that work is actually occurring. So again, it's this idea of conservation, right? If we're playing rock, paper, scissors, or we're playing some kind of game involving money, right? And at the end, some people are going to end up with some of the money, but some of the money is going to go to the dealer. We've got to account for that money that went to the dealer, even though none of the players have it at the end. I just made that analogy up. I'm not sure it's very good. But the point is, the work from friction has to show up on the side of the equation that involves the stuff at the end, because it's energy that was present at the beginning and is now going to be taken out of the system by the end. So it has to be added in order for this equal sign to still be valid. So here's the conceptual version of it. Here's the computational version of it, right? mgh for potential energy, 1/2 mv squared for kinetic energy, and then work. We're not going to focus on a possible equation for work because that force is going to be changing direction, and yeah, we're just going to leave it as W for work with a little f to say that it's the work of friction. Fortunately, we know everything else though, right? We've got mgh for the potential energy. Carl's mass is 32. That was given to us in the problem. We're on the Earth, 9.8. The height of the ladder was 4.8. Put all those together. We got the 1/2 mv squared. Again, Carl's mass is 32. His velocity was given as 4.5, so 4.5 squared, plus the work of friction. So we've got everything here except for the work of friction. We compute those, you know, again, we see a massive inequity, right? If we didn't have the work from friction showing up, we'd say 1250 equals 324. That is not equal. And the reason that's not equal is because a lot of that energy was taken away via friction, which is good, right? We don't want our children climbing up on slides and then coming off the end of the slide just as fast as they'd be going if they stepped off the ladder. That would be dangerous. So slides are designed to have a certain amount of friction. Of course, with wax paper, you can reduce that quite a bit. So we subtract those two, and we end up with the work from friction is 926 joules. 926 joules is how much work was done to Carl based on the fact that this is how much energy he started with, and this is how much energy he ended up with. And the difference in those is going to be what was taken away by friction. So that's a friction example. Here's a different example, one involving work and not a vertical work example like the ladder. So how much force is required to give a 45 kilogram vehicle a velocity of 6.5 meters per second if it reaches that speed in just 12 meters? So here we go, a rocket car that's gonna get us going really fast. So as we face these problems, we've got to decide how we should approach them, right? Should it be a energy problem? Should it be a work problem? Should it be a power problem? What is going on here? And you might see, oh, they gave me a mass, they gave me a velocity. This is probably going to be an energy problem because mass and velocity would give me kinetic energy. And it does. It does. But the key that we need to focus on a little bit in this particular problem is this idea that they're asking us for force. How much force? Okay. And potential and kinetic energy are never going to tell us force. So that should immediately alert us that this is not purely an energy problem. And the other thing here is that they gave us 12 meters. That's a distance. And again, I realize it's confusing sometimes, right? Because if it's a vertical distance, that would be a height, and that would indicate potential energy. But this is not a vertical distance. This is a horizontal distance. Presumably, we might know that because we know most vehicles move horizontally, especially if they travel that slow. So when we see force and distance, that should give us the clue that we should be doing work. So force, distance, and velocity, that says that work should be involved. In this particular case, they didn't give us a total value for work, so we can't just do W equals FD when we don't know F. So we're going to need to do the other way of finding work. Work equals change in kinetic energy, which is convenient because they gave us the kinetic energy stuff. So work is force times distance. Kinetic energy is 1/2 mv squared. So this equation turns into this equation, of which we know the D, we know the M, and we know the V. So we're good. All we don't know is F. So we proceed to plug in our known values, 12 for the distance, 45 for the mass, 6.5 for the velocity, and we solve for F. It comes out to be 79 newtons of force. So again, we're just working through practice problems here, reinforcing the concepts from the previous video of energy. And again, these energy ideas of conservation and work are allowing us to solve problems that would have potentially been unsolvable using kinematics because the accelerations are not always constant. This does not imply a constant force and a constant acceleration. What we calculated here was the average force being delivered. So one last slide of a couple of example problems. Cantaloupe of unknown mass is dropped from rest 3.4 meters above the ground. What is its velocity when it strikes the ground? So again, some of those important words that we've got to read and identify as essentially as numbers. If it's dropped from rest, then its velocity to start with was 0. So again, we've got potential and kinetic at the top, but as soon as they tell me that it's being dropped from rest, then we know that the kinetic part is 0, okay? And the potential is going to be something. And then when it strikes the ground, of course, its height is going to be 0. So in that case, we're going to get a 0 on this side and a kinetic on the other side. So again, we end up with the kinetic at the bottom equals the potential at the top. 1/2 mv squared equals mgh. Now, the concern that might be popping into some of your heads right now is, hey, they didn't tell us the mass, unknown mass. That's no good. The only numbers I know here are h, 3.4, and g. How am I supposed to solve a problem when I've still got 2 unknowns? M and v are both unknowns. Well, as we saw with the 65 kilograms of mass in the dropping off the ladder problem when we were figuring out how fast I would go when I hit the ground, the mass drops out. The mass cancels out. You divide both sides by m, and the mass cancels on both sides. So we simply bring the 2 to the other side, and we take the square root. So we're back to v equals 2gh, square root of 2gh. So v equals square root of 2gh. And we plug in our numbers, 2, 9.8 per g, 3.4. We get square root of 66, which is 8.1 meters per second. And you notice that's a little bit smaller than the ladder problem when I dropped off the ladder. But again, as we consider the fact that the mass drops out, if we are ignoring air resistance, the mass does drop out, and it doesn't matter what you drop from that height, the velocity it's going when it hits the ground will be the same. So the ladder was 4 meters tall, and it dropped, and we got 8.8 meters per second. This is only 3.4 meters tall. We drop, we get 8.1. So it's an interesting idea that this relationship here, v equals the square root of 2gh, is reliable in telling us our velocity, regardless. Example problem, got an archer here with a bow. he pulls the string on the bow back, right? This applies a force through a distance as the string tightens up and applies that force. So we want to know what is the velocity of the arrow when it leaves the string. Another case of distance and force being involved, and so this would be a work problem. So force, distance, velocity tells us we should be doing work and kinetic energy. So again, we get FD equals 1/2 mv squared. This time we're not looking for F, we're looking for V. But again, there's 4 variables. We've been told 3 of the 4. We're supposed to solve for the unknown. And so a force of 201 newtons times a bowstring distance of 1.3 meters. And this is not the length of the bowstring, this is the distance the bowstring is going to move when he lets go of the string before it stops pushing the arrow. Yeah, FD equals 1/2 mv squared. So we take the 2 to the other side. We get 2 times F times D divided by the mass. And that gives us our V squared, which is 1740. We take the square root of that, we get 41.7 meters per second. So that is the end of this set of notes. But as you know, very often in class, when we get done with our notes on the second day, I give you some practice problems to do to kind of test your skills and help you strengthen and reinforce those concepts. So I have posted a set of practice problems on Blackboard, and I'm now going to make a second video. I'm not going to attach it to this one, but make a second video for today of me going over the answers to that set of worksheet problems. But I would encourage you to download those problems, work them, do as many of them as you can. If you get stuck on some of them, then maybe watch my explanation from the beginning of those that you got right, and then pause the video and work the other ones again. The key to practice is, the key to understanding many times is to practice. So just seeing all my answers is not as helpful as you having the experience of having to try to do them before you see the answers.